Hello, boys and girls. Today I take you 10 years back or so, and I will review my master thesis. Here you see the University of Vienna homepage, and there you can find all the various theses. I'm not sure what the plural of thesis is in English. But in any case, we will get to back to that in a second. The name is Geometric Structures in Non-Commutative Emergent Gravity, and before I get into the review, before I scroll through the actual text and kind of explain a little bit what's going on, I will, as I often do, walk through a bunch of related topics that you can look out for if you want to make sense of it, or also, if you're just in general curious about the various subjects adjacent to geometric structures in non-commutative emergent gravity, right? So we can quickly open this. I think this was about, it's even 60 pages here. Diploma, but this was actually before the bachelor-master split. So in Austria, this is called Magister, which doesn't exist anymore. I was in the last year where there was still a Magister. It was basically a master title. It was not split into two. It was just here the Magister Naturalis, or what's it called? I don't even know. And this is together with my then advisor Harold Steinacker, and we also turned this thesis into a shorter paper that has a similar name, maybe a little bit less vague. It's called On Poisson Geometries Related to Non-Commutative Emergent Gravity, and if I recall correctly, this is about 30 or 40, or not even 27 pages. So there, this is a little bit slimmer. I mean, apart from it being in a different typesetting than my thesis. Let's scroll a little bit and find the relevant parts. Apart from that, it also doesn't have as long as an introduction and so on and so forth, and it's a little bit reduced. So I think here this is about, you see for some part it's translated, slimmed up a little bit. So you can also find it in the archive. As always, I have all the links to these texts below. This is my LinkedIn. You can find the thesis also here in this bracket here. There's my master thesis. There's also my PhD thesis. I guess at one point I might also go through that. So my master thesis was in essentially differential geometry, or Riemannian geometry in the sense of general relativity, while my PhD thesis is actually in plasma chemistry. So it's an extremely different subject, but yeah. I did my master's thesis, and then I already stepped a little bit away from academia. I didn't really want to get into the publish and perish line, even though I love, of course, research, and I read a lot of paper, as you know. I kind of wanted to not end up there, if you want to say it like that. I wanted to go a little bit into a more applied direction, and that's why I ended up at the German Aerospace Center, which is sort of the German NASA kind of, for my PhD. And now I work in another completely different fields, but okay. So this is the page of my advisor. Here you see his projects. Basically, my thesis grew out of one of his papers. I have it here on the next page, actually. So at one point in May 2010, he wrote this paper, Schwarzschild geometry emerging from matrix models. So he works in matrix models, which are an approach to fundamental, so high energy physics, where you, roughly speaking, deal with fields, and the fields are really this. You can imagine them as infinite dimensional matrices. They are non-commuting objects, and the remarkable thing about that is that you can take, more or less formally, of course, some semi-classical limits, and then it looks like some gravity is emerging, and these matrix models, there are various kinds of them. They're all sort of tied to some string theories, and you can take this limit, and then you end up basically both with something which looks like gravity and something which looks like more or less like normal quantum field theory, the standard model, and my thesis is in the gravity part. So despite the thesis being coming out of quantum field theory, if you want, I end up working just with normal, so to speak, Riemannian or pseudo-Riemannian geometry in dimensions that you can choose, because of course in string theory you already have more dimensions if you want. So this thesis is going to be about finding out things about gravities, Riemannian matrix, and if I say Riemannian, I always mean pseudo-Riemannian in the physics sense, and I do this in various dimensions as well. Okay, and so he wrote this one paper where he saw Schwarzschild geometry. This is a particular kind of general relativity solution, a particular kind of metric. I will say a little bit more about that in a second. And so he found, well, I will scroll through this very quickly. You have this matrix there, and he found some way to to squeeze that out of the matrix models. And then my topic for my master's thesis was basically, hey, takes some other interesting or standard or known or solutions of the Einstein field equations, basically the solutions of general relativity, various metrics that describe various scenarios in space, and try to find out what does it take, what for example, what conditions do we have to impose on the semi-classical limit of these matrix models to find this physical metrics, these physical general relativity settings. Okay, so and by the way, he does that basically. He is still working in matrix models, although I have not worked in the field since I left my master's thesis. Nevertheless, I really enjoy these Poisson geometries that we will see, and in general, I like differential geometry very much, even if I kind of slipped into the more hands-on computational side in the previous years. Okay, so what we will need to understand what the Riemann metric is. Obviously, I want to keep this video more or less short, so I will not actually explain anything about it. Not going to explain shit. But that's an ingredient. Then there is this very nice that I can recommend. Wikipedia page is also a little bit of a hidden gem, where you see listed a whole list of alternatives to general relativity. So this is basically, I suppose quantum field theory arose in the early 30s, in the late 20s, and then properly studied in the coming decades. And a lot of things were figured out in the 70s, 60s. But this is all quantum field theory stuff. Here we have alternatives to general relativity, to classical, quotes unquote, general relativity. If you don't know, basically classical is more or less synonymous with non-quantum. So despite from a common perspective, like normal people perspective, general relativity might be seen as out there. It's still in the classical domain. It's basically the same. In classical geometry, you use the same math as you can use in general relativity, especially if you play around with funky coordinate transformations. Then your classical mechanics will just look like general relativity. Apart from that in general relativity, you have genuinely curved metrics, blah, blah, blah. But then again, if you look at a very classical, simple problem that has some constraint, then you also have curved spaces. And if you have a Haar measure on some space like the quaternions, which you need for basic rotations, then you're also dealing with manifolds that are properly curved. So this is all basically the nice math, the non-quantum field theory functional analysis kind of math, where people don't actually know completely what they're doing from a mathematical perspective. Okay, so yeah, this is a very nice page because this like lists a bunch of theories, also like theories that came up before general relativity, like in the 1, 2, 3, 4, 5 years before that, like precursors, other metric theories. But of course, the like apart from the high energy problems and the problems that have also not been solved from other theories, like dark energy and whatnot, general relativity is more or less uncontested in its range of validity, and all these theories, like this page has like you must imagine it has like 17 like alternatives to general relativity, and they're all classical. You see the deep wealth of theories that didn't make it, or maybe some of them are even studied today. So I recommend this just as a like look into that if you're interested in general relativity, to get some history. And also, for example, if you if you go in Nordström, so there's for example this Nordström's theory, which is, as it says here, it's actually a precursor. So this is like a few years before general relativity. Also has already the kind of this metric set up. It's pretty interesting to read the history. Okay, but I'm stalling here. Yeah, Einstein fields equations are the equations that you must solve according to this general relativity gravity theory, and the metrics that I considered are basically all solutions of these equations for some mass density. What do we have here? Yeah, so in particular, here is a metric. So the Kerr-Newman metric is the most general asymptotically flat stationary solution of Einstein-Maxwell field equations. So here, this is about gravity with some electromagnetic fields. And here you have a table. That's why I got to the screen is too small. Okay, so I cannot show everything at once. But here you have the Schwarzschild solution, which is basically the simplest gravity solution with a point mass in the middle. And then you have, which at a certain radius describes a black hole. And then you have the rotating version of that. And then you have like if the point that makes for a black hole is or for this gravity field, this charged particle, then you have these various metrics. So for example, the Reisner-Nordström would be one which is charged. And so you get this kind of matrix, and this is also what we were going to see in my master thesis. Okay, I prepared this as well, but we already covered that. Then, since we're dealing with this gravity emerging from the matrix models, basically, let's say quantum field theory, you have there are some fields which are not of interest in my thesis, like the meta fields, if you will, and then you have the stuff that gives rise to the Einstein solution metric, the gravity. And so this is in the sense in which, of course, the gravity is emerging, and these objects are going to be some tensors, and the tensors, apart from the gravity, also give rise if you tweak the solutions in the right way, i.e. if you set the constraints that you want to look at, then you also have something like an almost complex manifold. So this is like overlapping with everything from analysis to symplectic geometry. And then you have here, in this particular case, in this context, in these theories, you have some J tensors that we will also like see when I browse through my thesis. And here I see some equations. I dealt a lot with these equations while I wrote my master thesis, and I spent so much time in Mathematica at the university and solving like differential equations, trying to find the conditions under which I actually derive the matrix that I want. And it's funny because I spent like hours and hours and hours solving differential equations in this half a year or so in which I wrote my thesis, and none of that made it into the thesis. So in the end, like you sit there for 2 months and try to solve numerically or with the symbolic tools some differential equations, and then maybe this gives rise to some ideas, to some analytical solutions, but in the end only the analytical solutions are what you see in the thesis, and so you wouldn't even see like the work that went into that. But I guess that's how it goes. Here then this is also like a theorem of symplectic geometry. This is basically a theorem in which relates, like, for this to grasp this, you must understand what a exact solution is, and what these D operators are, exterior derivatives. And in the end, what I do in my thesis is finding something similar for the spacetimes that I'm interested in. So I take these equations, which is in terms of a tensor, and then there are some natural conditions that I impose, and then it turns out, this means that these tensors must actually arise from some potentials. And so in that sense, I have an analog of the Boo's theorem. I don't know actually how to pronounce it. I think it's called the Boo. That's how Austrians pronounce these French names anyhow. Okay, and then there is a motivation behind also the matrix models and how they manifest then in the semi-classical limit. You may know that in quantum mechanics you have, if you look at the position and momentum, or position and velocity in one spatial direction, so for example in the x direction, then the observables, the from a functional analysis perspective, the operators that give rise to the expectation values for these physical quantities are non-commutative. That's what kind of makes quantum mechanics special among various stochastic setups, if you will. And so that you have the case that if you're just looking at one dimension, x and p, the position and momentum, don't compute. On the other hand, the momentum in this direction and the position, like the precision that you can measure, so to speak, the uncertainty that is given rise to by these operators, these commute with each other. So there's these commutation relations, the canonical commutation relations. I'm sure they are on this side somewhere. Yeah, here you have this is in one dimension. X and p are some object, in this case I times some physical number that is usually given the unit of action, so energy divided by times time, energy times time. I would like to see the canonical commutation relations for all 3 dimensions, because then you would see you get this delta 1. But let's canonical, come on. I'm sure there's a link to the that goes in the right direction. So this is of course the matrix mechanics text. This is basically the Heisenberg history of how people arrived with these things. But here is already expressed a variant in terms of matrices for the commutation relations, the fundamental commutation relation. And here you have this Kronecker symbol, right? So this basically says then that in these directions, for example, momentum, like if you look at measuring the y direction of position and the z direction of momentum, for example, then you don't have this commutation relation, but just if you look in one direction, okay. And also the various positions. So if if I is the index for like this 3 spatial dimensions, so you have the position observable x1, x2, x3, then these also all commute in quantum mechanics, right? Okay, so where I'm getting with this, the one idea that people had is, hey, let's look actually at a sort of generalization of the setup where you have, for example, position variables, like position observables in different directions. So for example, you look at x in x direction, and so x meaning the position observable, right, the component, and x in y direction. And what happens actually if you assume that these themselves already don't commute? So this is not the situation that you have in 101 quantum mechanics, but here you have actually that components of the position vector, if you will, don't commute with each other. And so you have an uncertainty in space directly, which gives rise, and you can speak about it in those terms, to a space which doesn't have any points, because you can actually not localize any points. And the idea was that if you have this set up, then maybe some issues bring together general relativity and quantum mechanics can be circumvented or resolved somehow, because you actually don't have a space of points. It's definitely a different space. So also just out of like curiosity, how does gravity look like there? And so we will have a situation where we are interested in commutation relations, where nothing commutes basically. In terms of algebraic geometry, you look at a variant of spaces with like coordinate functions, or if you're in a tangent space, like even like all the 6 functions on momentum and position for all 3 dimensions, that are actually like a completely non-commutative object. And so this is what we are going to deal with. Sorry. And here is this topic, this matrix theory set up, and as you see, it relates to string theory. This is the article. Here are the links to non-commutative geometry, which is in essence what I described just now. Here, this is framed as a theory in mathematics, also, although it's made use of in physics. And of course, you know, if you look at the Con's, like also a French name, Con's book, he has a book on non-commutative geometry. There's also in the introductory chapters a lot of physics talk, really mentioning kind of things I just talked about. And then also here the link to the EKKT matrix models. This is basically what the Steinacker, my previous advisor, is working in. Yeah, here's the non-commutative geometry page. You can pause and read this if you're interested, or just hit the link in the bottom. And then, since this non-commutative geometry exists, there's also the non-commutative quantum field theory. Of course, if you do quantum field theory, you're working in an Banach space with some operators and whatnot. So there's already a lot of non-commutative objects involved there. But what is meant here with the non-commutative is, as I just described, these canonical commutation relations, but between just the positions. And in this case, this is probably the 4-dimensional vector, so time may or may not be involved here. Given by something which is not the Kronecker delta, but it's just in some general theta tensor, right? And this is the object that I'm working with in my thesis, okay? Okay, and here a bunch of more related things. Okay, then there's the non-commutative standard model. I mean, these ideas are already a few decades old, I suppose, at least 2 or 3. And as you may know, there hasn't been too much under the sun that's new, I think. It's fair to say, in the last 1-2 decades. So apparently it didn't completely work out as the physicists hoped. But nevertheless, the people have published on this kind of stuff, like making the standard model non-commutative in the space sense. Okay, and finally, very related, and there is also like names like a while. Okay, but this has been a while. But also Kontsevich is got famous, I think, for work related to that, and he's a mathematician, but deals a lot with quantum mechanics motivated mathematics. And related to that, Poisson structures, and in particular the Moyal product or related concepts. And this is super interesting. I cannot really get into that for time reasons now. I'm already at 25 minutes and haven't not even started with my thesis now. But the idea here is that you take, for example, you take quantum mechanics, which is a structure with a more or less normal space, and then you have these observables and functionals that you can evaluate on the observables, and then you get expectation values, and that's how you do physics. And then here the observables are these non-commutative objects, right? And the idea is like, what about this? Can we do classical mechanics where you have a commutative coordinate ring, and then find a structure in this classical setting, in this classical differential geometry setting, like this is going to be the star product, which is a non-commutative object, which then makes the classical coordinate rings, if you use them with this product, behave exactly like the quantum mechanical observables. So you kind of define on the classical space this non-commutative product, which mimics everything from quantum mechanics. So this goes into that, because here, for example, here's one definition, and these pi matrices here, they also like sometimes denoted by theta, and then they relate to the theta that we just had. Basically, this is the first order non-commutativity term, right? So if h bar squared is approximately 0, if this falls away, then you're left with this product being the normal product of the functions plus some non-commutativity term, right? And so if you do the commutator with this product, you're left with I h bar and then this sort of Poisson structure, right? And I'm certain here we have the Wu theorem coming up, and then you also have, I'm sure, Poisson structures, and that's why also here why the name the name of the text of the archive version is on Poisson geometries. Okay, this is Poisson structure. This is a classical mechanic tool which also relates to quantum mechanics more directly. But okay, so this is the kind of the background math in the course setting in which I'm playing my games here, right? And okay, we can close this. We can close this as well. Can close this, and I will just go with my thesis actually. Okay, so let me see if I in 15 minutes can browse through this and sketch out what you will would see here if you go through it. 60 pages, as I already said. I dedicate this to my mom, of course. I also dedicated my PhD thesis to my mom because she's the person who will be most happy about it. So that's nice, I suppose. Should I read the abstract? I mean, I already described sort of what is coarsely about, but I guess it might not be too bad. Okay, so this work is a study of permissible Poisson tensors in non-commutative emergent gravity. And by the way, there are several emergent gravities. This is like the concept of getting Einstein gravity out of some other formalism does not only apply to matrix models or quantum field theory in this sense that I work in here. So there's also, for example, entropic gravity, where you say gravity really arises from entropic motions in the universe. And of course, since general relativity in its range of validity is right enough, this means that you have to find other frameworks which kind of boil down to something that looks like gravity. And matrix models aren't the only place where this happens, or where this seems to could possibly work out. Okay, so in this framework, in contrast to classical general relativity, the spacetime metric is not the fundamental object, but an emergent quantity which also depends on the functional algebra given by these non-commutative structures. A short introduction to the concept of non-commutative geometry and non-commutative emergent gravity is given. So this is the introduction that I will not dwell on too much in the following. The following investigations are devoted to solutions of the Einstein equations of motions for Poisson structures in the semi-classical limit of the so-called matrix models in Young-Mills type. So Young-Mills is the standard model underlying classical setting that is quantized to the physics that we know it to a very good approximation, and these matrix models that my advisor investigate also relate to that, but I don't have anything to do in this thesis with quantum field theory. One is naturally interested in solutions which are compatible with the certain physical spacetime metrics, of course, we're doing physics here. And then general results and calculation procedures for anti-symmetric dual solutions are deduced from spacetime in four spacetime dimensions and Lorentzian signature. So Lorentzian signature is means you are in n dimensions, usually 4. That's the classical setting anyway, and you have this metric, except it's actually not a metric because one sign is flipped, so you have this light cone thing behaving a little bit different than in plain Riemannian geometry. And here I speak of anti-self-dual solutions, but this is actually basically what I found out, what pops out if you give a more or less natural restriction on these semi-classical limits, and then you end up with something which sort of looks like electromagnetism in the differential geometric setting, as we will see in a second. This regime is formally analogous to the study of complexified classical electrodynamics on a curved spacetime. Okay, because you can do curved spacetime framing for the essentially purely differential geometric Maxwell electrodynamics that already exists, and then you of course also have the field strength on this physical world, and the field strength is some tensor. And in this case, we also have a bunch of tensor objects, namely these kind of theta structures that arise from this semi-classical limit that also then give rise to the Moyal product and so on and so forth. A solution on all manifolds which admit a conformally flat metric is computed, and previous results, like a solution for the Schwarzschild metric, are systematically rederived. So I started already with the knowledge that you can obtain this Schwarzschild metric, and I kind of generalized that. I gave the conditions under which you can also find other, maybe more complicated metrics. So I rederived that in a systematic setting because this was just a task to actually investigate why does this actually work out. And then also I found out along the way that conformally flat metrics, which are very simple metrics, also can be found there. This is basically, you have this metric tensor, which is like just a diagonal according to your signature, so Euclidean or Lorentzian, and then you just have one simple scalar function in front of it, and then you have this conformally flat matrix. And since the equation that I look at is quite complicated differential equations, if you dumb down things, you can also find solutions that look like that. Then higher dimensional cases, the higher dimensional case is considered where it is demonstrated how the additional degrees of freedom can resolve problems encountered in 4-dimensional case. So my advisor then was also interested in, for example, de Sitter space, which is always a hot topic, and then so I look at 6 and 8-dimensional settings, and there you have actually more degrees of freedom, and if you don't add more restrictions, then it's actually easier in a sense to find also solutions that fit into that. And that was also what he was interested in adding in the published paper. So this is basically that he found that particularly interesting, that he can talk about the Sitter spaces in his framework as well. Okay, then there's the abstract in German. Here are the chapters: Introduction, then Non-commutative Geometry and Physics. These are basically, these are just introductions, and this is also just a setting. Then non-commutative emergent gravity as well. I will basically skip these first 15 pages. Then I look at four-dimensional manifolds. I take the setting that I have just introduced and look at what does it look like in the most physical space, let's say the simplest, the Einsteinian sort of space. And then I go on and take the equation that I need to solve and look at it in 4 dimensions, and then have various sub-cases, solving the equations of motion. And then here they mentioned conformally flat ones, and then I look at radial symmetric metrics. This is very motivated by the treatment, for example, as you find it in electrodynamics 101, where I also say, oh, here's this solution that works out because it's rotationally invariant, and then you have this sort of framework. Oh, what happens if you demand the potential is only depends on the radius, and then I basically take a lot of inspiration from that and kind of go backwards. If you want the solutions, what are the conditions that you have to impose, and so on and so forth. Good. I fix some conventions that my advisor previously actually didn't fix in that sense, or not explicitly anyway. So usually you sit down and you work on things, and then you only then kind of discover, hey, what would actually be the best definitions, and then you can rewrite everything and it becomes much more slick. Okay, here's a motivation. I really don't want to get into that too much, but there is this situation with the so-called Landau problem or Landau quantization, where you look at some electrodynamic situation, which is basically classical, and you carry over these restrictions. There's a magnetic field involved in 2 dimensions. You have a 2-dimensional plane, and then what does it mean for non-commutative relations in quantum mechanics? And then you also find a sort of non-commutativity aspect just in this 2-dimensional plane. So you have x and y not being commutative. And I kind of recite this example to sort of motivate that thing that I already discussed through the Wikipedia pages before. By the way, sorry that I'm speaking so fast, but I don't want all these videos to take 1 hour. But I guess I try to reduce it to the interesting things. Then here I talk a little bit about while and these structures of some operators which also relate. This is all like introductory stuff that you have to list to give the context. I talk about the Moyar products, although in the end I just do differential geometry and don't speak much about observables, quantum mechanics, or anything like that. So I will not dwell on that either. The quantum field theory stuff that I also already discussed, and then comes some matrix model things, which is the property theory where my context arises from. And here I write down the action and what it means, but not actually relevant to my thesis, because I just take as a given that in the semi-classical limit, as it says here, you have a certain, in this case this is a Poisson bracket, being something non-trivial, some generic tensor depending on the space-time point. And so what arises out of this is you're more above, you start with this background metric, which is just this diagonal metric, and then you have this in the matrix model you have these matrices which become something like a coordinate ring in the semi-classical limit, and these then give rise to a metric, but that which is the effective metric, this is basically the metric object, the tensor object, which takes the same position as the metric in some other field theories. Don't know if I want to get to that. Yeah, so here we have some action relevant to these matrix models, then goes blah 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 blah, and you end up then with this spatial integral over this tensor, and then this inner product of the gradients of these fields. And in that sense, these sort of actions already like are familiar with, people are familiar with them, and then this G is a metric, and in that sense this thing is the effective metric. Okay, this is the effective metric, and the condition that I will look at in this, so here's some equation that pops up. This is a differential equation because this is a covariant derivative, and the condition that I will look at is, hey, how does the situation look like if we say that the metric, the in-between metric, the small g, which was like part of this derivation, actually coincides with this capital G, the effective metric. And this is sort of a setting. Okay, let's assume that should like simplify things a little bit. What are the conditions under which, in this case, we get something physical out of this theory, right? So that was of course the interest of my advisor. Okay, and then I go on and I step down into the like 4-dimensional case, and I do some computation, and like what does this condition enforce? I do some algebraic manipulations, and eventually I end up with like equations like this. And the funny thing is this, like I got the like. This is at the beginning of the thesis here, but actually this is what I got this like 1 or 2 months like just before I finished. This is actually a very late result once I realized, oh, there are some things that I did all along, and this can also be summarized in this sort of general approach. And if you look at it like that, then of course it must be like all my solutions actually look like this, where you have this matrix, component matrix, where the entries are like just the square roots and blah blah blah. So I did so much like Mathematica stuff, and I used tensor algebra packages, and in the end everything that ends up is like everything flows nicely just from the definitions like here in these 3 pages. Yeah, then if you are dealing with Riemannian geometry, then there's this sort of natural Hodge flip of tensors, and this you have covariant derivatives and all this, so this also ends up being relevant. And then here out of this grows some conditions, some like the condition capital G, small g, then kind of end up trickling down to being a condition on this theta tensor, to being self-dual or anti-self-dual. I ended up treating both the Euclidean case and the Lorentzian case, so basically the normal geometric case and the space-time metric case together, because they sort of only differ by a sign that ends up given a complex I here. And so this is one of the main conditions that keeps me following then along this thesis. So here this conditions there. This was already, I think, at least in a special case, evident in the paper that came before me. And then also something that not I have seen or introduced, but it was also already clear before. If you have this theta and then this G, then you get this J, and this J behaves like this almost complex structure in the sense that it squares to -1. Yeah, okay. Although I end up working mostly in terms of theta and the anti-self-duality. Okay, then here this is still the 4-dimensional like easiest case, and okay, I treat this Euclidean and Lorentzian cycliture apart from each other, and then we had this differential equation, right? And here then I discover, so this is basically my proposition that one of the main theorems then of the thesis. It says that these closed forms of interest on a 4-dimensional manifold with a Lorentzian matrix, which are the physical ones, that satisfy this condition that capital G, small g, are of the form, and then we see, these are actually given as the derivative of something. Like this is like in the differential geometry language, like closed and exact forms and this kind of thing. You can phrase things in these terms with this star operation that I just talked about, where the metric gets in, and there are these two potentials. And suddenly I have reduced the problem to like less degrees of freedom. I have only these two potentials. And then this means then the differential equation I had above is actually this sort of thing. And then if you are familiar then with the electromagnetic study, the study of electromagnetic fields in curved space-time in general relativity, this looks a lot of like very familiar. These are Laplacians on a curved space, and this the sigma object also was the sigma object that was already past part of what we saw above is also given then in terms of these two fields, phi and psi. And so this is these are then the Boole coordinates. So this is the theorem. I make use of that in the end by like solving the equations, that the simplified equations that arise this way. Okay, I will speed it up because I don't want to actually ever to try to stay under an hour. With this insight, I step into this physical case on 4 dimensions and see what implies that. Furthermore, then here I actually call then this f, like this object that I like pull out f because it like behaves it's very similar to electromagnetic field. Prove some algebraic relations that are imposed then on it. Use some fancy group theoretical language that I understand not today much better than I did when I wrote it. Okay, here I really I go with the electromagnetic language here. Thought that would be a good idea. I suppose that's true. Compute stuff. Like this is all derives like from these restrictions that are imposed at the beginning and the more restrictions that I impose on myself along the way. Here some lemma. This is still in the 4-dimensional case where I can make things much more concrete. This gets to like naturally some of the objects that are must be coordinate independent end up being this invariance that you may know from electromagnetic field theory. Okay. I will like just skip this. Here's some more fancy differential geometric language. I remember I think I like some of these things on these pages came to my head while I was in the cinema watching a movie, and I was it rolls in your head and you're not actually watching the movie, and then suddenly like under the shower comes your insight, and I was very happy at that day. This is very classical Riemannian geometry stuff. Okay, here I flesh out this proposition. I prove it that I already read out before. This is like literally these equations from that I also see in electromagnetic field theory in curved space-time. I was really into also like not going too much in coordinates, so you have a lot of like proper mathematical modern differential geometry language, unlike most of the books actually I read at the time, but I thought that's very elegant, I guess. Okay, more stuff that looks like field theories. I get some solutions, and these are just some generic comments on it, okay? And this as well, like who here in some special case I end up with this invariant being just a simple function of this is the determinant of the metric. Okay, and then actually getting to some more hands-on physical solutions. Here I recover the plane Moyal solution, which is like doesn't even depend really on x, at least in this in the right coordinates. Of course, if you change the coordinates and if you have these forms and you change coordinates, then you will get an x dependency because you chose strange coordinates, but they are in this nice coordinates. There's no x dependency on the tensor elements themselves. And then also see the conformal solutions are also can be squeezed into that, and so I have these conformal solutions that I think were not talked about in the paper that came before me. And then I take this equation that I had written down before, right, and I basically solve it by saying, what happens if we impose this electrostatic ansatz. I use a lot of knowledge from field theory again, And then I find out, oh, then this even reduces to this thing, and this is basically like a square of a gradient. And then here, oh, in this context also, the conformal flat matrix pop up again, and then I take the electromagnetic 101 route and find radially symmetric gravities or metrics. I say, hey, if I start out, I want a radially symmetric metric where these just depend on a function that depends on the radius. What does that mean? Like if I take this together with my differential equation, what does it actually impose for further conditions? And I do this, and I find out that eventually these phis, like of course you have this decomposition in where is it here? Yeah, the spherical harmonics. This potential must decouple like this, and then you get some simpler equations. And in this way, I eventually recover then. So, then this means that your metric function that you have assumed before in the metric must look like this in terms of this phi, some size and size. And in this way, I recover then also this care metric that my advisor saw in this text, and even make it a little bit more general and define the objects right in hindsight. I then have some nice plots. They are related to the Schwarzschild spacetime, and then here some more pictures. And then I say, okay, let's go away from a 4-dimensional case. Let's like a 2-n-dimensional case, and then I make some observations. What does that imply if you take Moyal-like Poisson structures? If you don't know what it is, I don't blame you yet now, but you can look it up. And then what does it mean for this theta and for the metrics that this works out? And then I observe, you can also get a little bit more general by doing this and that, and if you make this component bigger, then you must make this component smaller, stuff like that. And then I also look at the radial symmetric metrics, which are that was definitely also like having a cleaner look at all these ideas that were implicit in the paper already, and find out how this like general thing looks like. And generally this small comment on how to tweak this, and then finally comes this de Sitter thing, right? You have de Sitter spacetime, some two-dimensional torus, and how can we make this work with our conditions? And then I give a statement what has to happen that this actually works out. So there's some conditions. Okay, yeah. Okay, I know I hasted through that a little bit. I'm sorry for that, but the good thing is I'm actually done in under an hour. So that was my master thesis. I will most likely come back to talk about plasma chemistry as well, and otherwise in the next month I have planned to, on the one hand, deal more with constructive set theory and on the other hand with Clifford algebras, Quaternion algebras, and plane geometry as it's used in the classical mechanics, for example, as an outlook. Okay, so I guess that's that. Have a nice, mellow Wednesday evening.